presentation is entitled Making Sense of Hierarchical Log Data by Damon Wischik of Cambridge University.
Thank you. Because of the Cambridge schedule, if this were 4 months later, I'd say thanks very much to 4 wonderful master's students for having done all the work and produced results, but I don't have results, I don't have data to show, I'm afraid. That will be coming in 4 months or so, I hope. So all I have to offer is questions, speculations, challenges. Let me start by talking about data centers. Srikant talked about data centers yesterday. I think he and I, well, we're talking about the same thing. We're coming at it from radically different angles. It's just as well to start off talking about the overall shape of things that we're interested in. Here I've drawn a typical data center topology. This is called a fat tree topology. The little dots around the perimeter each represent individual servers, individual machines running code. And the cyan dots closer to the middle, those represent switches, which route traffic between the hosts. All of the switches in the central core will be connected to the wider area internet. So here's the data center. What happens in them? A request comes in. Let's suppose I log on to Facebook, I send in a request. It will be routed from the internet, me, to a particular server in the data center, to a front-end web server which has the job of processing my query. It typically doesn't have the resources to answer it on its own, so it will send it off. For example, it may fire off a subquery to the recent posts database to see what I've done recently, may send off another query to an ad server. The ad server may then send off another query to, for example, a friend graph database. So a typical thing, from my point of view, from the point of view of the outside, it's one request. From the point of view inside Facebook, there's some rather sophisticated code running all the way through loads and loads of sub-requests inside the data center, complicated structure to that code. Here's a different view of exactly the same thing. This is, I've got time going down. At the top, we see the transaction starting. At a certain point in time, it fires off a subquery to the left-hand line, the recent posts machine. Let me stand over here. Fires off a query to the recent posts. I've drawn that as a slanted line. It takes some time between when I send my request to that machine and when it receives the request. So these slanted lines represent TCP flows in the network, and the vertical lines represent just processing time of that job. So for example, here I've sent a query off to the recent post server, and in parallel, without waiting for the answer to come back, I'm sending off a query to the ad server, and the ad server then sends off another subquery and so on. So this is just another way of looking at computer code. This is really, well, I'll say now, this is, in my opinion, the core thing that makes societal networks interesting and challenging. There's the interplay between something like this, something discrete structured, something about people making choices about how to use a system, and a physical infrastructure which it runs on. So what sorts of questions do we want to answer in societal networks? Here's a sort of question that we might be interested in for the data center point of view. There's developer operations, DevOps. They'll be looking at charts about performance. They might notice there's a problem. Hold on, the response times have gone bad. What on earth is the cause of this? Did the network engineers do something? Did they install a patch which changed the way the network behaves and changes everything? Did the programmers change their code? Did they push an update which changed the way it behaves, which causes everything to go wrong? Is there some part of the system which has entered a state of instability where the machine, it starts churning, it does a piece of work, it gets overruled, there's too much coming in, it never has time to finish a piece of work before it gets to request the next one? Is it because of external factors like a change in demand? Or is it a weird knock-on effect? There's some change in this part of the system, and which changed the way that works, which had a knock-on effect to the part of the system I'm interested in. These are fiendishly difficult problems to debug because precisely of this interplay of code and infrastructure. Here's an example, true story. This is from several years ago. This is trying to help some students debugging a master's project. They had a peer-to-peer code base. It was for sharing information about an interactive whiteboard. It was running perfectly happy on their computers until suddenly it became horribly slow. It only ever became horribly slow when it was running on the campus network, not when they were running from home. And eventually, we diagnosed the problem. It was cunning transmission algorithm. It ended up sending a sudden cascade, 12 packets at the same time. When they were at home, these 12 packets, they were going over a fairly slow ADSL link, so the packets got spaced out. When they were on the campus network, the 12 packets arrived at the router back-to-back. The routers did not have big enough switches to cope with this, so it lopped off the final few packets. So that meant that the receiver never received what it was expecting, so it went into a timeout. So how on earth do you end up discovering this sort of issue? Well, let me give a slightly more precise statement of a problem. I'm going to imagine that we're collecting log messages, very similar to the log messages that Srikant talked about. The sorts of logs that I think it's plausible to imagine collecting is logs of flows. Logs of flows are something it's no good trying to insert instrumentation in the middle of the network because those switches, they have to work in nanoseconds. You'll never have the infrastructure to make them log fast enough. It's no good asking the programmer to instrument every single piece of their code because it's all they can do to keep up with all the feature requests. Whereas something like logging flows is something you can make a change in the operating system, tell the operating system, start logging every time there's a new flow starting, who started it and what machine is it going to. So you can imagine that sort of logging is quite easy to collect, or you can imagine it being built in as a service by Amazon, for example. You could also imagine that the programmer might typically place in certain logging statements every now and then. So this is the picture. If we have logs of flows and we know which process, which chunk of code generated that flow, which particular request, which transaction generated that flow, plus occasional programmer log generated messages, but we don't know the network state or the code. How do we diagnose problems? Just to repeat, why do we not know the network state of the code? You could say, well, okay, Facebook, you wrote the code, you own the network, surely you can debug it. But that's basically not how these things work. You have someone trying to understand why on earth the system has gone haywire. You have programmers who barely understand what it is they wrote last month, let alone what someone else on the team wrote. You have network engineers who they're off trying to make sure that nothing falls apart or burns. So it's not good enough to say you wrote it, you ought to understand it. We need to give people help. This is the state of the art. This is a dashboard from a company called AppDynamics. They were bought by Cisco a few years ago for, I think it was $3 billion. Their solution to this logging problem, they process logs very similar to the ones I described, and they say to the user who wants to understand what's going on in the network, you sit there and you manually annotate every server you're interested in. You manually annotate every single type of transaction you're interested in. And then the system the end user has defined buckets. The system collects data in each bucket. It reports aggregates across those buckets. So I think it works perfectly well if you're a real expert and you know exactly what's going on in your system. You know how to sit there and spend weeks annotating exactly which categories you want to collect data for. But it's not terribly useful. So this is a better way of stating the problem. Based on logs at some intermediate level of abstraction in a complex societal network, we want to have a system which is capable of achieving unsupervised learning. And the things that we want to learn about are what types of code are running, how is this particular bit of the code influenced by that part of the network? For example, that story about sending 12 packets back to back is influenced by certain types of switch design. And how does the network infrastructure respond? That other people using that small buffer will surely be interested to know, hey, because of this app, your traffic is going to get crummy service. So, right, this is a slightly more abstract way of stating the problem. We really are interested in ingesting vast amounts of log data and getting insight into what's going on. So this is probably a good place to say, how is this different to Srikant's story? Srikant's story, he was talking about data center, he was talking about processing logs. He was talking about a small number of events over long periods of time, and each event generated lots and lots of messages, so interest in statistical characterization. I'm interested in a world where each transaction, each agent going through the system, there'll be zillions of those all the time. Every single page request to Facebook is one of the entities I'm interested in. I'm interested in a world where we're only really trying to get fuzzy characterization of what they are. Think of asking, what are the types of people? That's the sort of question I'm interested in, whereas Srikant had finite innumerable set of events he wanted to probe. Okay, so I don't have answers yet. Still waiting for master's students, but I have hunches about where the solutions are likely to come from. So let me bring in some machine learning. I'm going to depict here a slightly simpler version of the story. The full version of the story, the code structure I showed you before, it had sending out requests in parallel, waiting for them to come. You can have, whatever you can write in code, that's the sort of thing that might be happening. I'm looking at a much simpler piece of code here which works in series. The request comes in from outside to this machine, sends a request here, waits for the answer, sends a request here, this sends a request here, waits for the answer, we're done. So that's the sequential version of the program. I'm just turning it sequential to make life a bit easier. There's no point trying to solve the full problem in all its generality when I haven't even got you data to show the solution to this one. But anyway, this is just an illustration. And this is what it'd look like if we, the 4 machines involved, time going down the vertical axis. What I'm going to do is I'm going to take this piece of code and rewrite it as a sequence of state transitions and control actions. So initial state 0 leads to an action saying send a request to host 5, or in systems programming speak, fork to host 5. That results in a state of computation here. By state, I'm basically thinking of this as something which captures the mindset, the intentions, the current state of program execution at a given machine. So based on the request which was sent here, it will send arguments, parameters, to a computation process running here, and that will induce a state of the machine here. That machine then makes a decision saying, I have finished my processing, I don't have anything else more to do. I'm going to emit the control action join, which means revert my answer, return my answer back to the person who requested it. And so we end up with a new state here, S2, which is the result of joining. This is just a way I'm choosing to represent what the program is doing. This machine was in state S0, fired off a request to that machine. It ends up in a new state, which is the result of incorporating the answer from that function. So this is just a way to take a piece of code, rewrite it as a string in a formal grammar. The reason I did this is so that I can use some quite cunning machinery by these people, Kuzner, Page, and Hernandez Lobato, called a grammar variational autoencoder. So now we get onto the neural networks. This is what they were trying to represent. It's ideas which sort of have come out of deep learning for natural language processing. But I'll tell you specifically the way, a model for understanding this inspired by the way they look at it and very much in line with the way deep learning people are trying to process these sorts of data sets. These are the actions, these are the messages. So think of this as the string in the formal grammar. I'm going to imagine there are certain functions here. F and J, corresponding to the fork and join operators I had on the previous slide. And each one of these functions, it takes in the previous state, it takes in the current action, and it emits two things. It emits a new state going to the right, and it possibly emits an answer. We're going to ignore the answers for most of this processing. So this is rewriting the fork and join computation graph. All of these are going to be vectors. In natural language processing, they talk about word embeddings. They talk about ways of converting a word in language into a high-dimensional vector. And they think of these as vectors. So these are neural network computations, multi-layer stuff, takes in a bunch of vectors, outputs some vectors, feeds it into another neural network function, E stands for encoder, produces a low-dimensional vector here, feeds it into another function, D, which feeds it into a playback routine here, made up of more function boxes. I need to write down an equation, I think. So here I've omitted some of the details. So let me just repeat. We're talking about state being represented as high-dimensional vectors. I'm talking about these messages, the words in my grammar, as being the actions as being embedded into vectors. And these red boxes, they're just computations parameterized by some parameter. And the overall machine learning exercise here is you want to train these red boxes in such a way that the output you produce here matches the input that you were given. This is a normal machine learning sort of task. You use backpropagation to say, I've written this the wrong way around. This is a typical sort of computation. You'd say, you define yourself a loss function. For example, here I'm going to treat P naught as a probability vector over possible actions, and I want P naught to have a high entry for the actual action which it's meant to produce, and so on. And you define a loss function which says, I want to maximize the probability of producing the output I actually saw. So this is an autoencoder. It's something which basically is aiming to take a string in a formal grammar, condense it down to a very low dimensional representation such that that thing can be played back to reproduce the string. So back to this picture, the latent variable Z that we get in the middle, assuming that we manage to successfully train the autoencoder, Z is a low dimensional vector, and it encapsulates all that matters about the code. It encapsulates the intent, the F functions. How is it that a particular machine decides to fork requests to others? It encapsulates the experience element as well. It says, based on the answer you got from a sub request, what do you do next? So in other words, autoencoders based on this sort of sequence business give you an unsupervised way to group similar transactions. And seems to me to make sense as a basis for visualizing, understanding how these data centers work.
So what is the input to the autoencoder in the message log? What do you give as input? I didn't quite understand.
It's these the actions. So when I look at a single transaction, I'm going to gather all the log messages that describe how that transaction was processed, and I'm going to convert them into a string. And I'm just going to say, can I build a neural network which takes the string as input and produces the string as output while going through a compression stage in the middle?
All the messages related to one transaction.
Yeah. Why am I interested in this? Well, basically, previously I was working on public transport data. You have train users who maybe decide, I'm going to do a commute. And the commute has a bus leg, then a train leg, and the train leg consists of taking two separate trains. I also was working with taxi data. Each taxi driver occasionally frequently has shifts. Each shift they'll do multiple rides, and each ride generates multiple GPS data points. So it seems to me this general picture of a fork and join style discrete structure occurs in so many places across societal networks. A really common feature is that when you're given the data set, you have a data set at a slice through this network. For example, for these commuters, we knew when they tapped in and tapped out of the system. We didn't know which trains they took. We didn't know, was this a commute, was this a leisure trip? For the taxi drivers, we didn't know, well, we were given a log of ride start and end times. We didn't know when their shifts were starting or anything like that. That's the sort of stuff that you'd hope to discover from the data. And then the other ingredient to all of this, you have the interplay between the discrete structure of something here and an underlying infrastructure. I haven't drawn on the neural network diagram, deep learning system, how to incorporate that, but that bit's more standard to people used to this sort of deep learning modeling processes. It's really how do you encapsulate the discrete set of actions chosen by a user, which is new in all of this. And so when the question of data centers arose, I thought that was really useful. The trouble with societal network data sets is you always got these problems about data access and privacy and reproducibility and so on. Just trying to get all the latent variable representation, all the comprehension of these things working, I think is hard enough. If we're working in a world of data centers, we've got the most controllable system that you can possibly have, especially if we're working with NS3 simulators. They're a wonderful laboratory to refine the techniques. So when it comes to actually analyzing these things for real, we can just transpose the techniques across. And the data sets I'd really like to see are every time you pay with a credit card, who are the big processors in the UK? There's, let's say, Barclays Bank. They seem to own about 40% of the terminals. So they have a control room somewhere receiving something like 40% of every single credit card transaction, debit card transaction. And so you can imagine building up an actual economic model of what people actually do rather than what economists think they do. A data-driven picture, a snapshot, which attempts to encapsulate in those latent variables the thought processes behind what drives people to do certain activities. You know, it's economic data transactions. They're not just logs. It's not I bought carrots, I bought onions, I bought chicken stock. It's I am going to invite people for dinner. To do this, I need to buy the ingredients for dinner. And to that, I need to buy the carrots and the onion. So much of human activity is in these hierarchical structures where there's intent going down, there's experience going up, and we basically need the tools to work with them properly. I'll skip this. This was, I promised in my abstract there'd be some data, but I was collecting data from students. There's online grading for one of the courses. So what I get, students have study sessions. I don't know how they think about how they approach the study sessions. The logs I get are every time they attempt a question, every time they submit a question. As an educator, you want to know how long did they spend working on it, which questions did they find hard, which questions do I need to rewrite, and so on. I thought in the aftermath of the Cambridge Analytica, I won't share the data. I won't be the Cambridge academic who's doing this. But this is the actual challenge. Based on log records at a low level of abstraction, what we'd really like to do is we'd like to infer what's going on in the mind of the user at the higher levels. Slightly more general than what I posed for data centers, but this is, I think this is really interesting. I think it's not implausible that we could do this. The reason I say that is that neural network deep learning structures like the sort I described have been used with success in natural language processing. You feed them a sequence of words, they end up able to reproduce the sequence of words. They end up able to comprehend in whatever sense a machine comprehends. They end up able to comprehend what the text is. The only way they can possibly do that is if they have encoded somehow inside their connection weights some concept of grammar. It won't be a straight top-down Chomsky-like concept of grammar, But if we can learn how to listen to what they have learnt, they will tell us the grammar they have learnt. Likewise, if we can train them on people data, they'll tell us the grammar of how it is that different types of students approach different questions, or different types of economic agents in a system approach what they're doing. So this is what I think is a fascinating challenge, fascinating class of data sets to work on, a fascinating set of challenges to try and comprehend what's the mass of meaning and grammar and structure in these data sets. Part of the answer will be, I suspect, deep learning inspired by natural language processing of the sort I was describing. There's also much more straightforward bits, semi-straightforward bits. The other parts of the solution that are needed are databases which naturally talk about this sort of hierarchical data, and user interfaces which naturally talk about hierarchical data. Basically, if you think about who processes data, there's this much data in the world, which is processed by the high priests of data at Google and Facebook and so on. And then there's this much data which is processed by everyday people who use Excel, who make all the decisions everywhere. And the trouble is, Excel and Tableau and all of its friends, they're completely and utterly wedded to flat tabular data. They're great at looking at a single level of the hierarchy, but if you ask the most moderately interesting questions which involve jumping up and down, identify all trips which go through a certain region, then color code all the GPS points from those trips. Those sorts of questions. There's just nothing which is available to people to use. Another ingredient which will be really handy for working with this sort of data, I'm going to call it the Selector Key Engine. Selector Key is a figure of speech. It says referring to the general by the specific. And if you think, when you read a newspaper story by a journalist, that's what they always do. They rarely start off with averages. They start off with a gripping anecdote, and they use that to illustrate what's going on. So what would that look like in a machine learning world? Let's say this is the picture of my full data set, and the red dots there, pink dots, which I'm afraid are barely legible, are my data points. The job of this autoencoder is to learn a low-dimensional subspace, a low-dimensional latent subspace, which basically captures all the interesting shape of the data. So now, if I come to this data set and I ask a question, tell me why are some transactions fast and some slow, chances are, well, it'll be some sort of division of the data set. Now, how do I then understand it? Trying to understand a neural network by understanding its parameters is just a non-starter. But this tells us a really useful way to look at it, what you should do, what the computer should be able to do. We've told it, I want to distinguish these slow transactions from fast transactions. It has discovered this through its deep learning system. It should be able to pick out 2 points on each side of the line and say, look at this one. This guy got fast service. Look at this one. This is very similar in many respects, but it got slow service. So I think that is a really useful tool for trying to comprehend very rich structured data sets. Basically anything that's related to human behavior is much more easily understood when you look at it as a narrative of individuals rather than as aggregates and parameters. Thank you.
Questions? If you think of those low-level records that have a very low entropy, just think of them as strings, because you say there is a structure there which can explain much smaller structure.
Yeah, I'm sure it would. At the level of strings, they certainly have very low entropy, but at the level of which ones come before which other ones, yes, absolutely, they must have really low entropy. Because there are only a finite number of things that happen. There are only 10 types of people in the world, that sort of story.
Thank you very much.